I will also send it out to, I'll send the link to everybody and we'll load it into a central place. Um, okay, so finally, okay, those distractions aside, I am close to the this one. Literally can't come any closer. But thanks everybody for joining. I know it's an inconvenient time for some of you, and you made time for this, and really appreciate it. The focus of this class has typically been for the new consultant and a person who plans to use it, somebody in the planning organization, etc. But while that's the focus audience, the primary idea is the primary uh, goal of this is to give them some idea of the math behind it without scaring people away from showing some huge complex equations, etc. So it is a little bit mathematical, but you'll see that it's basically the math concepts, and we will hopefully you'll get enough of it. And if you think it's not mathematical enough, there are subsequent classes, etc. But this is to lay the foundations of it. Um, Somebody who is not in supply chain may ask, why is MEIO important? Uh, One of the things that's going on right now is, as we know, we're going through some sort of economic uh, change or transition. And whenever that happens, people are less willing to invest in technology blindly, which is, in my opinion, a good thing. And they are trying to extract value from what they have currently, which is their where are your assets located, better forecasting, etc. In my experience, which ranges about 28 years, I've found that inventory is one of the easiest things to be successful at. So if whether you're a practitioner or a consultant, I always tell people focus on inventory first. It gets you your rewards. It takes away the pressure of having to deliver. It's also one of the things that you'll see requires not significant amounts of data, which, and one of the things that refrains that you'll hear if you're a consultant, regardless of industry, and especially with this current focus on digital transformation, is that there's a phrase which I hate actually, is data is the long pole in the tent. And that's great that it's the long pole, but again, so focus on things that I always start off with, focusing on things that require not so much data. And if I personally believe that if you take an approach of gradually building out your capabilities, you're going to be much more successful. And so without much more ado on my musings, I'm going to go into the slide. So this is the agenda. We're going to talk a little bit about the motivation approach. We're going to talk, the second and third sections are there, sort of pro forma, so that in case somebody's referring the slide deck at some point, they will have an opportunity to look at it. When you get the deck, you can say, oh, this is what you're talking about. There are two concepts that I'm really focusing on. There's this concept of demand rate, and you'll realize it's a very easy one. The second one is really what we're focusing on this time, is what we call effective lead time. And then we'll do some MEIO calculations. And there's a small hidden test here, and only one person so far has really successfully done it. I'm not telling you what the test is. That's the weird thing about it. You'll realize it's not a quantitative test, but I want to see. I actually expect this crowd to probably be to see the second or third person. Don't view it as, no pressure here, but just trying to uh, have people view things from a certain angle, and you'll see what it is at the end. And then we'll do a quick summary, okay? So again, this is intended to be a hands-on class, so feel free to participate, jump in with questions, stop the class, etc., and do the calculations yourself. I'll give about a minute or two for the simpler calculations. And if you can, if you can't, then, or if you're running short of time, I may just move on from there. So, okay, uh, motivation and approach. We are going to talk about the basic concepts and applicability of the MEIO algorithm. Understand what the inputs and outputs of a complete MEIO solution would be. And the third one, which is probably the major focus that I have here, is to prepare the user to apply the relevant concepts in real life. So I really think from this, after you take it from this, attend this class, one should be able to ostensibly literally apply it tomorrow if you're a consultant, etc. And I have done this. My team has done this. My teams have done this, and my clients have done this. And of course, the other motivation is it's a great opportunity for people to connect. And in larger classes, which have tended to be around 25 or so, but it was a more formal setting. People from various parts of the organization and from regions, etc., are able to connect, and they maintain those connections. So it's just an opportunity, especially during COVID times when I first started doing this pro bono, that people could connect. This is a vanity slide. This class, one of the reasons I brought it out on LinkedIn was because somebody thanked me for being a mentor, and I realized I have teachers and educators who have done a lot more than I did for this individual. So this is a list. I'm not going through the list of names, don't worry. But again, very grateful to everybody from my grade school teachers to my MBA teachers at the very end. Some of you will see some names which are the same. This is chronological, so so if you don't immediately see a name that's familiar, it's probably because it's not in alphabetical order. But that being said, thanks for putting up with this vanity slide, and I'll move on. So what should you expect to learn? What is the basic MEIO statement? That's one. The application of this solution to various real-world problems. This is more of a discussion, quite frankly. I will put out a slide because I did get some feedback from my earlier sessions where non-technical people, non-supply chain people attended. So I'll provide a background slide. I didn't want to just do it willy-nilly. I wanted to have, I just want to put a slide which would be explain it to a non-supply chain person. The foundational concepts, and this is important, the demand rate and effective lead time, the mathematical optimization problem, and this quote-unquote non-quantitative skill that you'll learn, which I think is really important, but probably not for this crowd immediately, but for people who apply it, etc. I think it's really useful. What will it enable you to do? You will be able to obviously understand if somebody is really doing MEIO, the key inputs, of course. How do you assess the outputs of an inventory optimization? And it would, again, this is a promise I make, that the user will be able to carry out basic analysis and do some preliminary assessment of your supply chain almost immediately. What it won't do is it won't teach you a software package like Blue Yonder. These are the names here are standard established supply chain planning companies. In this class, we're not teaching R or Python. Sometime early next year, we're teaching R or Python also, just basic stuff. But again, that one would be able to make it usable immediately. It's also not going to allow you to make a final recommendation on network design or an inventory policy kind of thing, but it definitely allows you to take the first step. And it's not going to make you an MEIO expert overnight, and I'm sure nobody's expecting that. So any questions? Please feel free to interrupt. We're all friends here, so no such thing as I don't mind interruptions. Shall I move on?
Yep.
Okay, thank you. So let me start off just to be very realistic from a mathematical perspective. It's a nonlinear mixed integer optimization problem, and in other words, mathematically, it's really, really difficult to solve. And the classic MEIO problem is considered to be NP hard. It's just a mathematical way of saying there is no formal way to solve it other than to calculate every single possibility. And even for let's say 1,000 item, several hundred node problem, they've said it would take about north of I think 100,000 years to do an exhaustive calculation from an optimization problem. Actually, since it's not linear, I would dare say that it's probably even more complex than that. But again, it's just basically supposed to be a really, really hard problem to solve, even with the advent of quantum computing, etc. So this is just a geeky phrase. And the next couple of slides are a little bit geeky, but I'm just doing it for those people. Well, it's actually quite candidly. It's more for you to refer later. And it's also quite, my team has used this in the past to offset arguments from potential clients, etc. Because there's usually, especially in high-tech companies, there's usually one PhD who wants to ask some questions and takes into the mathematical domain. So we just have some points here which would you can use for later. Please do not focus on this too much, but I'm just going to go over it for formality. We use this concept here called demand rate, and we, in the rest of this class, and for subsequent classes, we're going to represent it by the letter lambda, and we're going to assume it to be constant. There are ways to overcome that assumption, and we'll talk about it later. So if your demand rate is lambda and you have a time interval t, you are we assume that the demand is probabilistic, and it follows a distribution Poisson lambda t. Again, nothing really that affects any of the calculations that we're going to do in a major way. If you forget this slide altogether, that'll be fine. At least for this class, we're assuming that the lead times are assumed to be constant. In advanced MEIO, we will be talking about how to overcome those assumptions, or how do we adjust for those assumptions. So intuitively, again, just by the virtue of the fact that the mean is, we're having a rate of lambda, the mean or average demand in a time t, this is very intuitive. If your rate is 1 per month, so in 2 months you get 2. So it's lambda times t. So that's an intuitive statement. The variance, because of the fact that we're using a Poisson distribution of the demand in time t, is also lambda t. That's just a mathematical artifact, which we are going to use. Again, there are modifications to this. The next one is what we call normal approximation. We will be using it, but the formulas are given in this, and it's you can actually do all of this in Excel. The normal approximation for a Poisson lambda t is normally distributed with the mean lambda t and a standard deviation square root of lambda t. We will be using the next 3 a little bit. At the mean, the cumulative distribution function, which is the cumulative probability. So what it means is basically 50% of the demand. If you measure, let's say the mean is 100, 50% of your demand is going to be less than 100 and if you have one standard deviation, so if your one standard deviation is 10, then 84% of the demand is going to be at mean plus one standard deviation, which is 110. It's going to be 84.1. And cumulative distribution at 2 standard deviations away is 97.7. Again, if this sounds too geeky, don't worry. We actually provide all this information to you in subsequent slides. So, but this is pro forma. I have to do it just for the sake of, okay, for some reason. This is a list of the symbols that we'll be using. The only thing here that you'll have to remember here is, firstly, what is the target stock level? It's the level that you recommend you stock to at a location. For example, if you say at a location A, it has a 95% fill rate. 95% fill rate means you're able to satisfy 95% of the demand. We represent it as a TSL, subscript 0.95, which is and A. It's, again, really not it's something hopefully everybody will pick up along the line. I'm not going to spend too much time on this, but the other quirky thing about this, or not quirky, but it's a standard assumption which all software packages and all mathematical models support, is the supplier is assumed to typically provide an unlimited supply of the part. So you have some way of providing it in an unlimited amount, of course, subject to lead time restrictions. So if your supplier is going to take 2 years to make something, then you just include that in your lead time. Okay. There's this concept of safety stock. Safety stock is stock that we hold because even though you expect a certain amount of demand, it's to deal with the variability in demand, etc. So it's stock that you hold to prevent stockouts or unexpected variations during your replenishment cycle. A stockout is a term which is you use when no inventory is available to fill an order. So I know I'm zipping through this a little bit fast, but broadly speaking, is everybody kind of sort of getting a hang on this? Even if you don't get 100% hang on this, that's fine. I think you should be able to get the rest of the class. But are you okay with so far what I've been teaching? Any complaints? Funny Indian accent, something like that? Well, given the
No,
fact that
we are good.
good.
I think I'm good.
Okay. Anybody else?
I'm good.
Thank you. Okay, I know two is not a majority, but I'm going to.
Yeah, I'm good too, Naresh. Sorry.
Thank you. Thank you. Okay. So I will caution you that the first 30 minutes might seem a little mundane, but it's again, remember this is to teach junior consultants who have not seen some things also. They are within the scope of this. So I know most of you probably know this, but let's just go over this as a refresher. So if you have no variability, okay, so this is what you learn in your first course in industrial engineering. If your lead time is, let's be represented here by LT, how much should you stock up to? You basically stock up to whatever your demand over lead time is. So if your lead time is 100 days and you have, your demand, there's no variation in your demand. Let's say it's one per day. Guess what you're going to stock up? You're going to stock 100, right? Because why would you carry, if it's, the 100% probability, it's fixed. There's no variation. There's no advantage in carrying more than 100. And why would you carry 99? That means you have a stock up, right? Means you want to capture all of your demand. So the first upper left-hand part of it, I'm assuming there are no questions, but if there are, I'd be happy to explain it. Does everybody understand that? The basic stocking policy, no variability. Everybody gets this, right?
Yeah, I got you.
Now, this explains why the second part, the bottom part, explains why you have stuck out, because you have variability in demand, right? Means most of the world is what we probabilistic, or it's variable. I'll try to avoid using jargon like stochastic processes, etc. But basically, things do change over time. You don't. Nobody knows for sure it's going to be 100, 105, 110. So you carry a little bit more, and that's done in your safety stock. And your safety stock buffers you from reduces your chance of a stock out by having a little bit more. And how you decide that safety stock is something that within the purview of the larger MEIO course. There are many reasons why you may carry a certain amount of safety stock, but again, the basic rule is, if you think about it, is you carry enough because you want to capture some demand, because you're making money off of that demand. You're making profit off of it. Obviously, if you're not making any profit off of it, you should probably think about why you're even in the business. But the underlying rule is you carry safety stock to make sure that you don't miss out too much of your demand. Now, I've just shown a little bit of dip into that safety stock level. It can go, you can empty out your safety stock as well. Just from an experience perspective, if somebody, in fact, one of my clients, which is a Fortune 10 company, they were under extreme pressure to rationalize all the IT projects, and each IT project had to sort of prove their worth. And this is an age-old technique which surprisingly has been abandoned by some companies, especially the larger ones. But they basically, if you aren't dipping too much into your safety stock, so if you saw that little dent in that safety stock, which you can, the second dive there, if you don't dig deep into your safety stock, it probably means you have too much safety stock. So if that dent is minimal, it probably means that your safety stock is too excessive. Your safety stock at some point or other should not necessarily go to zero, but it should definitely have deep dives. If you're just barely scratching going into your safety stock, then you probably have too much, because now people may say that's a good thing, and most planners actually like that, but really it means you're carrying too much. And that company actually literally sitting in a conference room for 2 days, and I would love to say I'm the guy who inspired it. Actually, I suggested something like this, but more mathematical. But they literally looked in all the safety stock of their top 100 items. By Thursday, I remember this. They did it Thursday morning. It started Wednesday afternoon or Thursday morning. By Friday afternoon, they claimed they reduced the safety stock levels by $10 million. So and this is a Fortune 10 company. Okay, so um, you can imagine uh, the effectiveness of this. So to me, that's one thing, is it's a validation of the fact that um, correctly applying inventory optimization techniques is um, not is a very quick source of getting putting value to your customer or to your company. Okay.
A quick question, Naresh, on this. If some company is not getting into the safety stock or putting a dent into safety stock, wouldn't it be like we are carrying more cycle stock as compared to safety stock?
That is true. That's an indication actually that you're forecasting. So you're right. If you're not dipping into your, what I meant by dipping, scratching your safety stock was if that dent into your safety stock isn't too deep relatively, then that is an indication that your safety stock is excessive. What you're saying is, let's say the third spike, if everything is like that, the third, not spike, whatever, reverse spike, if everything is like this, it is an indication that your forecast error is high. So that's a very astute observation. You're absolutely right. Then you're probably over forecasting your demand. So in fact, statistically speaking, there's a correlation of a little bit. By the way, I'm not the PhD in statistics.
I'm sorry,
Right?
I'm hearing Sujan. Yeah, fine. There's
Hello?
a lot of background noise.
Is that me?
No, I think it's Sujana. Thank you.
Okay. Okay, thank you. Sorry, I personally didn't hear that, but thank you again for cutting that. Thank you for muting. But do feel free to uh, you know, to ask questions. But yes, very astute observation. It's basically a sign of forecasting bias that if you're not dipping into it, as in the third case, because you're not even going into safety shocks, shows that you're over forecasting the demand. This is again for people who aren't very familiar with the statistical aspects of it. So again, this is something that we talked about, and this is what we call the cumulative distribution. So this basically says at this particular point in time, which is the mean, 50% of your demand is equal or less than the mean. We're going to use this a little bit. So one standard deviation away. So if you calculate the variance, etc., and you assume that it follows a normal distribution, which seems to work for most cases, and there are ways again to adjust for it. But to keep things simple, one standard deviation away, we get 84% of your demand is got to be equal or less than this value, and two standard deviations away, we get about 98% of the demand. Okay, so any questions? Thanks for the active participation, but any questions so far? Guessing not. So let me move on. Okay, summaries. Okay. So based on what we talked about, right? So if you go to any standard textbook, if you give lead time demand and you have some variability, you should be able to do this. You saw at least intuitively how you can do the first one. If I give you a demand and you know what the lead time is, you should be able to figure out what whether you want 90. If you want a 98% fill rate, it's basically lead time demand plus two standard deviations, etc. So the left hand part you should be able to do. Okay. I'm going to ask you the second one, the middle one. Doesn't look as simple, and I dare say, and so far nobody's contradicted me, that this one probably most people would not know how to do, at least at this in this uh, at this particular point in time. The third one, which is what happens right now, I'm just talking about demands, right? What happens if you have reverse flows, like repairs and returns? It's called reverse logistics, by the way, but if you have reverse flows, because right now I'm just talking about the demand and it being met by a supplier. what happens if I have lead time variability? What happens if I have high demand variability? And remember, I assumed that the forecast rate was the demand rate was constant. What happens if I have time varying demand rates or demand forecast? So my promise to you is the second one, which looks a little bit complex. You would be able to do this. And my statement, and so far nobody's proved me wrong, is that you can do this in 30 minutes with enough time for a coffee break, water cooler talk, and maybe even 2 chats, and get done. So my goal is to solve this particular problem by the end of this class very quickly. Okay, and I'm claiming that all of you should be able to do this by the end of this class. 3 we will get to in the next class. Okay. And here, look, this is what we call a 3-echelon network. So there's 1 level, 2 level, and 3 level. So echelons, I didn't get too geeky on it just because when I throw in enough terminology, people lose track of the whole thing and they focus more on the terminology. But this is called 3 echelons because it takes 3 from the supplier all the way out. It takes about 3 levels. So that's one. And you notice that they have variable lead time. The lead times vary from location to location, and the demands vary from location to location, a whole bunch of stuff, right? So, but we are going to be able to solve this that's my promise to you, in less than 30 minutes with the time for coffee break. So, first, let's talk about the first thing. We are talking about demand forecast in an MEIO funnel. So everybody talks about demand. We are going to talk about demand rate. The intuition is very simple. If you have a demand rate of lambda, then the average demand over time t is lambda t. So I'm not doing anything really fancy here. Average demand over lead time, obviously, if its lead time is L, using symbols here, then your average demand over lead time is lambda times L. And remember, we said it's Poisson distributed. Again, we're not going to use we're not going to see this or confuse people with this concept, but we're going to do Poisson lambda L along the way. So why do we focus on demand rate, Poisson distribution, etc.? And this is actually meant for consultants. Probably nobody in this class really cares as much, but maybe if you do. One is a mathematical model. Again, remember those PhDs who sometimes attend and they ask all these concepts. When you say it's Poisson, it gives you some certain mathematical properties. So this is one property we'll use. Don't worry, it's going to be very intuitive. If there are 2 lambda streams, the 2 demand streams coming in, one which is distributed Poisson lambda 1, the other one which is Poisson lambda 2, you can, if they're coming into a location, the resultant demand stream is Poisson lambda 1 plus lambda 2. That isn't the case with many other distributions, but it is true with Poisson distribution. So that's one, it's a mathematical reason. The second thing is from an estimation perspective. Since this is a single parameter, means lambda, okay, I can usually get a reasonably good estimation of that with 5 to 8 data points. People often come up with these really, really complex models, and there are people infinitely smarter than me who have really, really complex models, and we have 500 variables, etc. Guess what? For 500 variables, you need at about 25,000, 30,000 data points, which in most cases you don't have. With lambda, you can get a reasonably accurate, if you're just using a Poisson, you can estimate your lambda, which is the only parameter you really need, with 5 to 8. The next easy distribution to calculate is the normal distribution. And a normal distribution has 2 variables, a mean mu and a standard deviation sigma. And that requires about 20 data points for mu and 30 data points for sigma. So it's, you need about at least 30 data points on demand, etc., so to get a good handle on that. So when you have, in supply chain, things tend to be a little bit variable, a little bit hard to get data. With this approach, you can get a good estimate and, again, a very usable estimate from there. From a calculation perspective, MEIO algorithms, which we'll see, change the lead time to calculate the TSLs. And you'll see that in a minute. Using a demand rate makes the calculations easy. So again, this slide, not really immediately relevant to you. It's just ammo for you in case somebody asks you some questions, etc. It's something which one can show to them, and the estimation part usually gets people quiet, and then the mathematical model is just to show some degree of completeness. I will move on to the next slide because I don't think this is. So let's talk about it representing demand forecast in the MEIO context. Firstly, just a quick sanity check. Am I going too fast? Am I talking in too weird a way? Any comments? Everything okay?
Sounds great.
Okay.
Yep.
Okay. So this is not a big change. Okay. So instead of talking about demand forecast, we're talking about demand rate. So if your monthly demand is 3, and we assume a month has 30 days, then lambda is 3 divided by 30, 0.1 units per day. Not really a big deal. If your lead time is 10 days, then immediately we can say the lead time demand is 0.1 times 10. So it's 1 per day. Not really a big deal. And what happens is if you have a location which gets a demand of 0.1 per day, then the subsequent upstream location, which feeds that, which supports that location, gets a demand of 0.1 per day. It's just a flow through, right? It's people who've done engineering. It's similar to Kirchhoff's law. What comes in has to go out. So if a location is getting 0.1 per day, it's probably sending a subsequent demand of 0.1 per day upstream for the upstream location to satisfy. Now, if a location has 2 demand streams of, let's say, one at 30 per month and another demand stream of 60 per month. So think of it as this location, this circle represents a distribution center, and it's supplying 2 stores. One store is coming in at a 1 per day demand. 30 per month, has a forecast of 30 per month, and the other location has 60 per month. So 1 per day, 2 per day. Then the combined demand, and this is a Poisson property which we're using, but this sounds very intuitive. You don't even have to know it's Poisson. If it's 1 per day and 2 per day, then the subsequent upstream location gets 3 per day. Does that make sense so far? Everything kosher?
Yep.
Okay. And so what is the key learning here? Demand rates are additive. The TS and the how much you stock at a location is determined not by individual streams, but is by the cumulative demand at that location. Okay, so I'm not trying to solve that 1 per day or 2 per day. I'm just looking at the cumulative demand at that location. Simple enough, I think, for everybody. So if there are no questions, I will move on. But again, the concept that I used here is lambda sum. The total arrival rate is the sum of the arrival rates, and then if your demand is distributed Poisson, your demand is distributed Poisson lambda, etc. Okay, so moving on. For some reason, okay. So let's talk about some conceptual things now. Usually in a class, I call out names, but I don't want to make people feel awkward. And for those of you who've done MBAs, and I think about 3 of you have probably done it here, the format is to call on people in the class, but I will not do that here. But feel free to jump in and help with the calculations at any point in time. So if we have one location and has a single item, okay, it's carrying only one item, and the demand rate is 20 per day, and the lead time is 5 days. So your lead time demand it's simple, right? It's 20 times 5, 100. So it's 100. How much should I stock at that location? Should I stock 100 units? Anybody? What would you do if I tell you it's 20 per day and lead time is 5 per day? How much would you stock?
Does it not depend on how often you ship from upstream node to this
That's the lead time.
location?
That's the lead time. No, that's a misconception, because it's your lead time, and we can take that. I'll give a more detailed example in next time, but it's always you're always focusing on lead time. It's not how frequent you use, because if let's say it takes you 1 year to make something, right? So even if you ship every day, it takes you 1 year to make it, then you better have 1 year worth of lead time. Because let's say your demand is 0, 0, 0, 0, 0, that's fine. But now you get an order for 5, then you need to have some amount, right? Does that make sense what I'm saying? It's not how frequently you ship. It's actually literally the lead time. How long does it take for you to procure that item and ship it? When people think of candy, people think, yes, I'm just shipping it, getting it in a day, even if it takes me 5-day lead time. But it's not that. And I'll give a counter example to that, maybe at the end of the course. But right now, I would tell you it's not the frequency of shipment. Okay. But that's a great question, because that everybody assumes it's how frequently you ship. But right now, if your lead time demand is 100, should I stock 100 units? Or more, less?
Yes, 100 units considering there is no demand and lead time variability.
No, so that's a great point. I never said there's no demand variability and there's no lead time variability. I'm just asking if your lead time. Remember, so I'm assuming that the demand rate is 100. This is, let's bring it closer to real life than the non-variable thing. So let's say this is, I'm just asking Jaina and in a general conversation, hey, I've got a demand of 20 per day for this, and it takes my supplier 5 days to get me the item. How much exactly do I carry? So remember, 100, Sujaina has hit on a good point. 100 is the mean, right? That's your lead. This is your demand rate is an average. And your lead time, it means, let's assume that's fixed at 5. So right now, 100 is just getting you average. So think of what an average means. Average means 50% of the time you're more, 50% of the time you're less. So 50% of your fill rate, if you stock 100, is going to be 50%, because 50% of the time you're going to be more than 100, right? Does that make sense? So it's the mean. We have to take into account demand variability. And here, because it's Poisson, we just have a formula here right now. It's the square root of lead time demand. So 100 units gets us a 50% fill rate. If I wanted an 84% fill rate, remember, so the formulas that are here, by the way, so at 84%, if I wanted 84% fill rate, so that means 84% of the time I'm able to fill the demand immediately. I have to go 1 standard deviation away. And in this particular case, because we are assuming Poisson, and we can, let's assume Poisson for now, there are ways to adjust this very easily, but to keep the class short, you can, so it's 1 standard deviation. So if you wanted 84%, it's square root of 100. So 100 plus 10, 110. And if you wanted 98%, it would be 100 plus 2 times square root of 10. That would be 120. Make sense? Yes.
Yes. Yeah.
Everybody okay? Means we're all friends here. So just if it's not clear or I'm not explaining concepts clearly, do push back. Or
So just a quick question, Naresh. So
go ahead.
I had a quick question. Sorry, I got muted. So if the demand variation is not Poisson and it is standard, you just change the formula for the standard for the normal, right?
Right.
ZSTD root L, that is only change.
That would be there's some nice mathematically elegant ways to do it, which are
Okay.
simple. The idea is, again, the idea of this entire set of C classes is to take concepts and be able to deploy them almost immediately. So if you don't want to assume it's Poisson, you want to assume it's something else, or there are ways to either have put some adjustments in the Poisson distribution so it applies, or you can just say it's normal. But finally, the idea is to find the 84 percentile point on a distribution point. I don't want to get too geeky on it, but yes, you have to just change something.
Got it. Thanks.
And the good news is that for well over 150 years, people have been working at good approximations of this. So remember, the normal distribution was discovered sometime in the late 17, I think early 1700s, late 1600s. So really, really smart people, typically monks in abbeys, who are like literally would sit down and do all these calculations, and much before the advent of computers. So they've figured out multiple approximations, and thanks to Google, all of us can be much more effective. I mean, what people took 50 years to do, we can probably do it in 10 minutes. But okay. But everybody okay on this so far? This should be, I know that for some of you, this is probably intuitive, but if not, does that make sense? Shall I move on?
Yeah, Naresh, I'm good.
Yep, I'm good.
Okay, so let's do a quick class exercise here. And there's a method to this, why I'm doing this. So again, I have a demand rate of 20 per day. So the first one has a lead time of 5. Second one, I have 25 per day. And the third one, I have 40 per day. Does somebody, do you just want to do a quick exercise of what I should have to get a fill rate of 98%? The first one I think we did, right, just now?
Yeah, first one is the same thing, right?
First one is 120. We know that because the mean is 100 and then plus 2 times square root of, so can somebody do the second and third very quickly? If you have, if you don't have Excel handy, it's fine, but let me just give the class a minute. And see what goes from there. I'm sorry about the typo. It should have said 3 locations. I haven't. I think it didn't save my. I know I caught this before, and I thought I'd save the changes, but sometimes I make the changes, but I forget to save the. Anybody want to be so bold as to give the answers? Okay. Well, let's just do this, right? So I made the correction. Okay. So we have 3 locations. We know the first one is 120. The second one we know is so we know it's 25 per day. Lead time is 5 days. So your lead time demand here is 25 times 5, 125, plus 2 times square root of 125 times 5. So it's about 147.36, and it gets to 140, right? Simple enough. The third one, which is we have 40 per day. So it's 40 times 5 plus 2 times. Okay, here's a typo again, but this.
Yeah, there is a typo there. Yeah. Okay.
Sorry, I'm probably using an older deck. I must have. But it's the same. The number is right, 21.90, because it's this part is right, and you get about 222. Okay. Everybody okay on this? I'll update the slides to reflect the correction. Sorry about that. Everybody get this? The math on this? This should be 40 times 5. That's all. Any questions? No? Yes?
I think I'm good, Naresh. Yeah.
Yeah, it's clear. Yeah.
Okay.
The calculation on the third one would be around 229 is what I think, because square root of 200. But yeah, it will be slightly different. But yeah, all good.
Okay. Sorry about that. Since we're all friends, yeah. Like this. Yeah, you're right. It's 14 point this thing, right? So I think it's this. Sorry about that. I'll get put in the exact numbers later. Thanks again. Sorry for this. My OCD is forcing me to. Okay. So everybody get this so far? No questions, right? Okay. So suppose it went for the location for the lead time for location C went from 5 days to 10 days. The demand rate is the same, okay? What's the TSL for C at a 98% fill rate? I'll do this myself here. So it's 40 times. So your lead time demand is 40 times 10 plus 2 times square root of 40 times 10. So that's very conveniently 440. So what is the key learning here is the stock level that you have at a location does affect your, is affected by the lead time. That also affects your safety stock, right? That the safety stock is 2 times square root of lead time demand. Fair enough? Simple enough?
Yes.
Yeah.
Okay. So I know that people are sort of saying, hey, I didn't get up early in the morning to get some basic math here, which I could probably do. Let's start making things a little bit simple, a little bit more interesting. So if you look at this slide here, I said, will I take exactly the same demands, which is 20 per day, 25 per day, and 40 per day. We'll consolidate it into one place, into one warehouse, okay, or one location supplying that whole thing. Lead time is exactly the same, which is 5 days. And let's calculate how much you should stock at location D to have a 98% fill rate. And if you look at it, so again, because these numbers are additive, it's 20 plus 25 plus 40. So it's 85 times 5. And that's 425. Okay. So that's your lead time demand here. Plus 2 times square root of your lead time demand. And that comes out to be about 20.61. So it comes out to be 467. Everybody roughly okay with that? What I've done so far? Everybody understand what I've done here, right? I've taken them up, added them up, and everything else is just wrote, right? But you'll notice here, it looks very similar to the previous problem, but instead of having, if you look at the previous one, if you added them up, it would be about 504. Hopefully that in the math, it factored in the mathematical errors, but or it was correct. I had errors taken care of, but still, it's a significantly larger number than what we're getting when we combine the demands into one location, and it's 467 units. Okay. So what have I done here? The only thing I've done is I've moved all these demands to a single location. My lead time demand is actually, if you look at it, is exactly the same. It's 425. What happens here is because I am combining the demands, I'm getting a lower standard of deviation, a lower safety stock. Any idea as to why I might need a lower safety stock?
Standard deviation, like risk pool.
Right. There's this concept called risk pooling, and people who worked in the finance industry, I think I know at least one, they bring things in together. The idea being that the variations in one tend to cancel out the variations in others. So and this actually happens in life as well. And there's in fact, canals and a lot of the areas which have multiple water streams, etc., and even for internet traffic, they use this concept called pooling, which is the idea is that not everybody goes to a 98%, the extreme high levels of demand at one point. So they when one tends to be high, there's a reasonably good chance that one of the other ones will be low, etc. So you're not going to see all the highs at the same time. So there's a cancellation of risk, and the fact that these variations in demand tend to cancel each other out is to take advantage of that, we use a concept called pooling. So it's risk pooling, and again, it doesn't reduce the total amount of demand that you need, but it does tend to reduce the safety stock or the risk. And so what is the key learning here? Pooling doesn't reduce the total demand. It only reduces the safety stock that you need. Okay. So that's an important concept. And that's what actually one of the benefits of using MEIO is when you have a location which is supporting maybe 500 sites, etc., then rather than you'll try to bring all of those demands in together because they tend to cancel each other out, if that makes sense. Does that help you? Does that make sense? So I already saw, you can already see by pooling this demand, I have reduced the inventory by roughly about 8%, right? Does it help? Any questions? Deepak?
No, this is good. Yeah, makes sense.
So
Totally.
again, nothing really particularly complex, and quite frankly, I wouldn't be surprised if you're saying, "Hey, okay, great, nothing major so far, but good revision, etc." Now let's start getting into echelons, right? We talked about multi-echelons, so let's talk about that. So now let's look at this problem, and we've done some version of this just a minute ago. We have one with a demand of 20 per day, and its lead time is 20 days, okay? I'm putting in a second echelon here, this location B, and it supplies location A, and the lead time from A to B is 5 days, and the lead time, but in this particular case, I'm not stocking anything at B, okay? So the fill rate is, what do you think? If I don't stock anything at B, what do you think the fill rate is going to be at B? If nothing is stocked at B, what percentage of the demand from A will B be able to satisfy?
It is essentially same as scenario 1 where you have total lead time of 20 days.
Right. So essentially, if I'm not stocking anything at B, then what the demand
50%
have to basically go down, be satisfied by S, right? So it's essentially like a pass-through demand, and one can argue that the fill rate at B is 0% because I have nothing, right? Everybody get that?
Yes.
In the third scenario, if you read it, a supply from B has as many units as A will ever need. Okay, so I'm keeping at B. Don't worry about what that number is, but I'm assuring A, no matter how much you need, I have it. I've got you covered. I'll get it somehow, or I have it on stock, etc. And you will not have to wait for this. Okay, so I'm trying to figure out what I would have to stock at A for a fill rate of 98% in each case. Okay, so we agree that the first one we've already seen, right? It's 20 per day, lead time of 20 days. So we've seen that before in a previous example, but let's just do that. But does everybody get what I'm doing or at least understand the problem that I've put forth in this particular example? Am I losing you? Hello?
Yes.
Okay, let's do the first calculation. We agree that the first calculation is quite simple. Do we agree that it's 20 per day, that's the demand coming in. Lead time is 20 days. So it's 20 times 20, that's your lead time demand, plus I want a 98% fill rate. So 2 times square root of lead time demand, right? So does everybody agree with this number of 440?
Yeah.
I'm sure you get that type of here. Everybody agree to this?
Yeah.
Yeah.
The second one, as was pointed out, B has nothing. So it's just a pass-through demand. So for A, the effective lead time, and I'm going to introduce this concept now, the effective lead time is 20 days. Do you agree? Because I'm not going to get anything from B. The fact that B is there, it's just a pass-through. So it's 15 plus 5. Do you agree? Everybody? Effective lead time is 20 days?
Yeah.
No questions there, right? Anybody disagree?
No questions, I guess.
No. Yeah.
But at B, in the third case, B tells A, don't worry about it. I've got you covered. So as far as A is concerned, what is the lead time? The effective lead time is 5 days, right? Does everybody agree?
Yeah.
So what I'm going to stock at A is significantly lower because now it's just waiting 5 days. I'm not telling you how much I'm stocking at B, but I'm saying as far as A is concerned, it is going to stock only 120 units. Does everybody agree to that? Because it's 20 times 5 plus 2 times square root of 100. So,
Yeah.
okay. So what's the lesson here? Well, we have intuitively rationalized, all of us together, that the upstream fill rate, that whatever fill rate you have at B, affects your downstream levels, right? Sorry, I probably jumped a little bit ahead. We agree here in the middle case, the fill rate is 0% for B. So fill rate of B is 0%. In the other case, fill rate of B is 100%. So we've solved two cases, and we've seen clearly it affects how much you stock at A. So we agree to that. I mean, does everybody see that my fill rate at B affects my TSL at A? And I've given you the two most intuitively obvious cases, which you didn't need to know anything fancy about it. One is a 100% fill rate, one is a 0% fill rate. And we can see that it affects everything all the way from 440 to 120. Right? Now, this is where we're going to start becoming a little bit smarter. And it's not very difficult. What would let's say I had a fill rate of B at 50%, or if I had a fill rate of B at 75%. Now, how much should I stock at A, right? And this is, now we're getting into one fundamental building block of MEIO. Because before this, everything was single echelon optimization, setting it up for this. But now you can clearly see, this is getting a little bit more complex. Okay, any ideas as to what I could do in this particular case if I have a fill rate of 50% or 75%?
So this is going to change the effective lead time.
It's going to change the effective lead time. So
Essentially.
yes. Okay. So let's look at this first example. Right? So if I say the fill rate of B is 50%, and we're going to solve it for 80%. So do you agree that 50% of the time, because the fill rate is 50%, A has to wait only 5 days, 50% of the time. 50% of the time, it has to wait 5 plus, and has to wait another 15 to get that, right? Because there are two lead times. So 50% of the time, it's 5 days. 50% of the time, it's 15 days. Everybody agree?
Yes.
So the effective lead time, would you agree, is 12.5 days? Because I've just done the math here. 50 times 5 times 0.5 plus 20 times 0.5, it's 12.5 days. Agree? Does everybody agree that's the effective lead time a day?
Yeah.
So my TSL at A is now, if you ask me, it's your lead time, average lead time demand. So it's 20 times this effective lead time of 12.5 plus 250 plus 2 times square root of 20 times 12.5. So it comes to about 282. Does everybody get that?
Yes.
Yeah.
Simple enough. It's not, the calculation itself shouldn't be hard, but did you understand what I did? I calculated an effective lead time and I just used that, right?
Hey Naresh, I was not able to get the effective lead time. Please, can you explain again?
Okay. So in the previous, do you agree that 50% of the time A has to wait only 5 days because the fill rate is 50%. So it means 50% of the time it has enough to meet any demand from A. And 50% of the
Yeah.
time, it's going to say, hey, after waiting 5 days, it's no, I have to get it from here. So it's another 15 days. Do you agree? So it's the lead time, 50% of the time, it's 20 days. Do you agree?
Okay. But I have a question here is like, why are we doing this 5 times 0.5, adding an extra 5 times 0.5?
Because it's this 5 days to go from here to here, and plus another 15 days to go from here to here.
So the effective lead time should be only 5 plus 15 times of 0.5, right?
No.
Why are we getting an extra of 5 times 0.5?
So the supplier is not, the way this network is structured, great question, by the way. In real life, there may be some other changes, but the supplier is providing it to B, and then B sends it to A. And so for B to get it, it's 15 days, and for A to get it, it's another 5 days. think
okay,
of this
okay.
as Singapore and think of this as a port in Mumbai. Okay, and this is, let's say, Nagpur, or let's say it's Delhi. So people who might not be familiar with India that much. So to go from 50% of the time, the port in the Bombay location can give it to you immediate in 5 days. So it's there. But now 50% of the time, if it's not there, then it has to come from Singapore to Mumbai, and from Mumbai it has to go to Delhi. That's the assumption. Now you can say that you can directly ship, etc. And those are modifications that you can make to the model. And there are some smart ways to do that. But right now we're assuming that the item goes from this represents the demand signal, but the shipment would be from S to B and from B to A. So it's a great question, and I will thanks for that question. Also, I'll actually include some explanation of that in case it wasn't clear. Okay.
I have based on this, I have a question on the previous slide.
Okay.
So so this one,
Okay.
not this one, the earlier one, like we were calculating effective lead time when the fill rate were 100%. Yeah, the previous one.
Yeah.
Yeah. So here it should be, if we do this,
So basically says
the
that
second case.
Mumbai has everything that it has. We're not talking about how much B is stocking, but we're saying the location in Mumbai has as much as A would ever need. So A is not going to say think about Singapore.
Hmm.
A is saying he doesn't worry about where it's coming from, right?
Okay.
So it's only 5 days.
No, the second case, like then the lead time should be 5 plus 5 time. Again, we get 5 plus 15. So it should be 25. Then
No, 20, right? 5 plus 15. 5 plus 15, 20. So let me put it this way. So let's say Bombay doesn't carry anything at that location. So but A has to get it from Mumbai. So Singapore will ship it in 15 days, 100% of the time. And then it'll take 5 days for Mumbai to ship it. Right? So it's 20 days.
okay.
Make sense?
This makes sense. I'm really sorry, but can you explain the later case where we have 50%?
Yeah, no
Just
problem.
once more.
Repetition is good. Not a problem. So 50% of the time, any demand from, let's say, A is Delhi, I'm just going to use that again if people don't have an objection. So from A, 50% of the time, I get it in 5 days. 50%
Okay.
of the time, I have to wait 15 days plus another 5 days. Because B is going
Okay.
50% of the time, B is not going to have it.
Okay, got it. It's not the case of fill rate is not 100%. I got it. Yeah.
Yeah, this
Thank
is the case of fill rate is 50%.
you.
Okay. So we use 12.
Understood. Yeah. Thank you so much.
And Naresh, in this case, why can't we say that 10 per day is going to come from B? And then 10 per day is going to come from S. So for half of the demand, the lead time is 5 days, and calculate the safety stock for half of the demand, and then calculate the safety stock for the second half, considering the lead time of 20 days. I did the calculation. Obviously, it's not matching, but
No,
what?
Then you're getting it's still A, how it comes. A doesn't care where you're not doing safety stock on them separately. You have to do it collectively, right? A doesn't, from a demand perspective. I know what you're trying. Not a bad idea at all. But the reason it's not coming out to be the same, you're still keeping the pools of inventory the same. Whether from A's perspective, whether it's coming from Singapore or it's coming from Mumbai, which is location B, it doesn't care. And it's whether you break it up that way, mathematically. Okay.
It will never add up. I get that, yeah, because of the pooling.
But the reason is because you are separating out the safety stocks. You're making them two separate demand streams. Then you have the effect of pooling.
Yeah. Sorry, yeah, got it.
And from A's perspective, it doesn't care where it comes from, right? Means you don't say this has come from, because if it's going to go on the shelf at a certain rate, right? So, okay.
Yes, go ahead. Yeah.
Okay. So just to be complete, the TSL at B, because it's a 50% fill rate, right? Remember, 50% is this one here, the stock level that you need at B is your lead time demand. So your lead time demand here, your lead time for B is 15 days, okay, for B. And it's at a 50% fill rate. So your TSLB is 20 times 15. So this is this formula which is in this gray box here. So it's your lead time demand. Does everybody get that? For B, it's 300. That's what I'm going to stock here to be at a 50% fill rate. And for A, it's 282. Everybody kind of sort of get that?
Yes.
Yeah. Got it. Okay.
Yeah.
So Naresh, just one quick question just to extend this, and I will not take much of everyone's time here. So if you have two suppliers, S1 and S2, where you're doing a sourcing of 50% each, so it's mathematically you can just do 0.5 of lead time, right? For each of those.
Yeah, it's your effective lead time. I mean, that's
Yeah.
So it's a very nice thought. It's actually a little bit of an advanced thought because just to get a little bit geeky, and I'll stop that. The typical structure which the mathematical models use is what we call an arborescent structure. So it assumes that everything it's like a tree structure. So a child has only one parent kind of thing. You're talking of multiple parents, and it's actually very easy to solve because that's what you do in internet networks and designs, etc. In supply chain networks, for reasons that are unclear to me, people have chosen to do it a certain way. But using the effective lead time, the calculation would be the same.
Got it.
And I know
Thanks.
this because I've designed telecom networks, and the calculations roughly come out to be the same. But
Sure.
Again, that's a great point, and it's a nice change, and maybe something I can use in the advanced concepts class. But here I'm just trying to establish a certain calculation methodology. Okay.
So in this, the only safety stock is the 31.6, and that you're carrying at A. There's no safety stock you're carrying at B.
That's
because
I have a 50% fill rate.
50% fill rate, right?
Example, but in the next example, I am carrying a safety stock at B, okay, which is the 75% fill rate.
Yeah. Okay. So effectively, if you didn't have the location B, you would have carried a safety stock of 40. Now you're carrying a safety stock of 31.6 just because you have an intermediate location.
Yes. Okay.
Yeah.
Okay. So now let's say B has a fill rate of 75%. Okay. So 75% of the time. So again, sorry, I'm just jumping ahead of myself. I'm just trying to keep track of the time. Okay, so we have enough time. So 75% of the time, B is going to be able to satisfy the demand. But I want you to calculate what the TSL is going to be for 98% fill rate at A, and what should the TSL at B. Okay. Sorry. Okay. For location A, would you agree that 75% of the time, A has to wait only 5 days? And 25% of the time, it has to wait an additional 15 days, which is a total of 20 days. Does everybody agree with that?
Yes.
Mathematically, that makes sense, right? 75% of the time, B has enough. Its fill rate is 50%, the 75%. 25% of the time, it has to this thing. So your effective lead time is 8.75 days. Okay. And if I use that and just use our formula here, which is given on the left-hand side, you can see that the TSL of A is 20 times 8.75 plus you do the math on it, comes to about 202. Now, because I have a 75% fill rate here, I have to carry some safety stock, as Deepak astutely pointed out. It's an additional formula here. This is the expression that you use. It's 0.67 times square root of lead time demand. And if I do that, I have to carry 312. So instead of carrying more inventory at A, I'm basically putting more inventory at B. Okay. But you can see now, I've proven to you two things, right? I've proven to you that your fill rate at B affects your stock level at A, and your I've given you a mathematical way to tell you the impact of that fill rate. Fair enough? Everybody agree to that? And it's a very simple calculation, all in all, right?
Yeah.
Okay. If you have any questions, please don't hesitate.
Just curious, Naresh, how did we get the 0.67 factor?
I went to the normal tables and
Okay, from the table. Okay, got it. Thanks.
because I used the normal approximation, right?
Yeah, sure.
But again, just on a side note, I would like to point out all this can be done in Excel, right? So you don't need any fancy software or anything like that. You don't have to buy anything, at least to do what I've done so far. Okay, so and I've gone from one echelon to two echelons. So now let's make it a little bit more interesting. Let's add another echelon. Why not, right? We're good with 2. Let's do 3. For A, so we have a 3 echelon network. Fill rate of C is 90%. Fill rate of B is 75%. And I want to figure out what stock level you need to have here for 98% fill rate, and also what the stock levels at B and C are. So this is just a mathematical exercise. It should be relatively simple, but in the interest of time, I'm going to give you relatively short periods of time to do it. If this was a classroom effort, would probably take like a 3-minute, 4-minute break. But if you guys are okay with it, we'll walk through it rather than spend a lot of time doing it. Is that okay? Because we want to get into the more exciting network kind of thing that I'd shown you before. Is everybody okay?
Yeah.
Okay. Just a quick sanity check. Are the concepts being explained clearly? Am I speaking clearly enough? Are these slides clearly enough? The 2 typos which are slipped by despite being caught multiple times. If you can forgive those, is everything else okay?
It is excellent. Yeah.
Okay. So for A, let's talk about A, okay? Because that's why we're really aiming for 98%. So we agree that 75% of the time, the lead time is 5 days. Do you agree? The demand is met in 5 days. That should be obvious, right? The fill rate of B is 75%, so I should be getting it in 5 days. Okay? Nobody disagrees with that, right? Okay, I'm assuming silent as assent in this particular case.
I cannot hear Naresh. Is it just me?
Sorry.
I lost.
Yes, same here.
You can't hear me? You can't hear me?
Now we can.
Okay.
No.
But
wow.
before we couldn't.
Yeah. Okay. So we agree that 75% of the time we can get the stuff in 5 days. The other 25% of the time, do you agree that now the remaining 25%, okay? 90% of the time I can get it in an additional 5 days, right? Because this fill rate is 90%. So 25% of the time you're going to go into this part of the network. And do we agree that in that time, so when it comes here, 90% of that, the demand that comes here, I can meet it in 5 days. That's what it says, right? Fill rate of B. Okay, this is another type. Good Lord, what am I doing? I must be using an older slide deck because I can't imagine so many typos. But does everybody get this?
Yes.
Does everybody get this? 25% of the time, 75% of the time, this demand is met. The remaining 25% of the time, in that 25%, 90% of the time, it takes me an additional 5 days. Do you agree? To get the demand. Yes? No?
Yep.
And do we agree of this when it's not met here? So again, that 10% of the time, it takes an additional 5 days to that. So it's like, so the effective lead time, if you look at it, is 0.75 times 5 plus 0.25, which is the number of times it goes here, times 0.9, because 25% of the time, and of that 25%, 90% of the time, it takes 5 plus 5. That's this plus this. Do you agree? That's 10 days. And then of that 25%, which goes here, another further 10% of the time, it takes 10 days. So it's 5 plus 5 plus 10, 20, right? Everybody get that?
Yeah.
Yes.
Okay. So now the effective lead time is 6.5 days. Okay, because it's 0.75 times 5 plus 0.25 times 0.9. By the way, you can type this up and check in Google or whatever. in the search bar, you can type in, does the calculation. Again, my apologies for the numerous typos. I might be using an older deck, which I might have deceived myself. And do we agree that for the effective lead time at B, okay, as far as B is concerned, it's 5 days, 90% of the time, and 10% of the time, it's 5 plus 15. Does everybody agree to that? For B.
Yeah.
Okay, so that turns out to be 6 days. Okay. No issues there, right?
No, clear. Yeah.
Now, those of you who've done engineering or taken in India, we call them entrance exams, etc. Josh, I think you're also have some Asian connections, so you know that there are these exams and you have to keep rearranging terms. So if you look at this EA, I can actually rewrite EA as 5, which is the lead time from here to here, okay, plus 1 minus fill rate of B, okay, times effective lead time of B. So look here, see what I'm getting. I'm just rewriting this. So this 5 is, I can get it explicitly. There's no fill rate mentioned here, but 1 minus fill rate, which is this 0.75 times effective. This term is the effective lead time of B, right? 1 minus fill rate times effective lead time of B. Just look at this mathematical stuff. It turns out to be very easy. Does everybody agree?
Yeah.
So this is the cool part. I have now got a formula here where effective lead time of A is the lead time from B to A. I'm not even mentioning the fill rate right now, plus 1 minus fill rate of B times effective lead time of B. And this is going to be incredibly, incredibly useful to us. Okay? So, but does everybody agree with this formula that I've shown you?
Yeah.
Yes?
Yes.
Yeah.
This is the formula that's going to make a difference for us. And it's, again, not a very complex mathematical, nothing here. I've not made any major assumptions or anything. So guess what? I'm just going to do this very quickly. TSL of A is 20 times 6.5, anyway. So this is just pro forma calculations. I've calculated the effective lead times for A and B from the previous slide. Sorry for jumping through a little bit, but it's 6.5 and 6 days. So I just do the calculation here, 20 times 6.5, it's a 98% fill rate, 2 times this, 153. This is a 75% fill rate, so it's 0.67, and I get a 128, and 2 times 10. Now this one, the effective lead time is 10 because there's no probabilities or anything, taking 10 days flat. So 2 times 10 plus, and it's a 90% fill rate, so it's 1.28 is that normal value thing. I should probably have put that as well, but you can see that it's 290. Okay. So this is just a simple calculation that we've done. Okay. So if you're okay with that, I'll go to the next part. Everybody okay?
Yep. I'm good.
Okay, remember I promised you something. I made a rather bold claim, and now I'm showing you something that looks quite complex, right? And if I had given this to you at the very beginning of the class and asked you to solve it, I'm sure everybody in this class is smart enough to solve it, but I don't think any of you would have said you could do it in that promised short time that I indicated, right? Like, which is, again, half an hour plus time for coffee plus time for water cooler talk, etc. So shall we go ahead and solve this? I'm guessing the answer is by de facto yes. Maybe there's not a choice there. So anyway, so what I do want to solve it for the forward locations at 98% fill rate, which I've indicated here, and I've given fill rates here of 0.5, 0.75, etc. So each location has a fill rate, and what? Let's just quickly review what we've learned. We've learned that the demand rates for multiple demand streams arriving at a location are additive. Let's keep that in mind. the effective lead time is not dependent on the demand rate. Remember that when I've calculated the effective lead, when you looked at the effective lead time calculations I showed you, not one of them you had some like a lambda or any of those terms in your calculations. The effective lead time is not dependent on the demand rate. And we've also seen that there's a very simple formula for effective lead time for a location. Okay. So unless there's some strong disagreement to that, I will go to the next slide. Folks, are we good?
Yes.
Okay. So let's just look at one part of the network just to simplify it. It really doesn't make much of a difference. Actually, let's go to this one. So let's stay on this slide for 1 second. So we see that A is at 10 per day. So what I've done is something which when you take your high school exams and you do that, like your electrical networks, etc., you just add this up, right? So from A it's 10, A to D, so D gets 10, E is 40 per day. So you look at H, what is it? It's 40 plus 10. So it gets an effective demand rate of 50. That's the additive part of it. So all I'm doing is I'm just going, traversing each graph very quick, each line very quickly from one node to another. 10 per day, 10 per day. This is 10 per day, 10 per day. And 20, this becomes, the total demand here becomes 20 per day. If I look at G, it's 20 per day. So I'm doing this in a rather monotone way, but my voice aside, this 20 plus 20, this becomes 40. So you go to the next location here, this 10 plus 40 becomes 50. So I've basically done, what have I done? I've done a very easy right to left traversal of this network, right? And it's a simple addition. It's just literally going down to the node, seeing what's coming into it, and just adding it up. Nothing really complex. But I have now the demand rates at each location. This is not very difficult, right? Everybody agree?
Yeah.
So now let's do effective lead time. So let's look at the effective lead time of H, right? So do we agree that the effective lead time of H is 10 days? There's no the fill rate here is 100% because it's a supplier. But so if it's 10 days, effective lead time of H is 10, right?
Yes.
Do we agree the effective lead time of D is 5, which is this lead time from that formula that we had, right?
Yeah.
Plus 1 minus fill rate times the effective lead time of H. Do we agree that that's also 10 days? Because it's 5,
Yes.
this number, plus 1 minus fill rate. Let's look at effective lead time of A. I have D, it's the parent. 1, that's the one here, plus 1 minus fill rate, so 1 minus 0.75, times effective lead time of D. So 1 minus 0.75 times 10, so we get 3.5. So I have very quickly calculated I looked at the time, in about 3 minutes, the effective lead time for A. If I have the effective lead times, guess what I can do? I can calculate TSLs. This is, H is 50%. So we look at the total demand, it's 50, that's coming in at H. We got it in the previous slide. I didn't want to crowd it too much, but it's 50 here, okay? Times 10, so that TSL of H is 500. TSL of D, so we know that the demand is 10 at D. 10 times 10, which is this effective lead time, plus it's a 75% fill rate, 0.675 times this. So it's 106.7. I'm going to round it up to 107. And A, we know the effective lead time is 3.5 days. We know it's a 98% fill rate. So the demand is 10. 10 times 3.5 plus 2 times square root of 10 times 3.5 comes to about, okay, 40. I'm just rounding up. That's the protocol that's followed typically in industry. So I've done 1/3 of the network in 3 minutes. And okay, 5 minutes including explanations. But if I wasn't talking, do you see how easy the calculation is? Any questions? Am I zooming over things? We have time. If you want, I can go over some of this. But is this calculation very clear?
This is clear. Yeah.
Yeah, it is clear.
So this is the beauty of it, right? So if you were to write, so for those of you who have a little bit of a programming bent, I'm not asking you to write code by any stretch of it, but remember there was one pass here. So from a code perspective, where I basically just totaled up all the demands at each location, right? And that's just a right to left traversal. And then I just did a left to right traversal where I was calculating effective lead time. And you can, in 4 minutes, I calculated 3 nodes. And I guess there are a total of about 9 from what I recall. So I think it would be equally easy, in fact, even faster to do these other ones. So I think I can stand by my promise. You can do this in half an hour plus time for coffee and water cooler talk. But do you see how easy the calculation is? Yes, no?
Yeah, this is good,
Yeah.
Naresh. Yeah.
So, and look, I've not made any major approximation of assumptions here. This is standard assumptions in any MEIO package, etc. Right? That means, or any, if you buy it from any commercial thing. By the way, this approach is typically used in most commercial software. Not this math of it, but the additions and all that sort of stuff, right? But what you'll find is most MEIO packages don't calculate effective lead time. They don't. They ask you to figure out what it is, etc. So, but there's something missing here, right? What do you think is missing? Means, have I achieved my goal?
There are two things, Naresh, that I had a question on. One is we started with the assumption that the demand follows Poisson distribution. So do we need to validate that somehow? And the second one was, how do you decide the fill rates?
Okay, so the first question is, usually you're going to get 5, 10 data points. It's not going to be, you can assume any other very complex demand, but you're not going to be able to estimate what those parameters are, right? You need, in the finance industry, the telecom industry, you can assume what those things are. And the good thing about the Poisson is you can approximate almost any distribution within Poisson or a sum of Poissons. So that's the good part. But again, in supply chain or in most non-financial, non-telecom related stuff, when you're doing these kinds of things, a Poisson is a reasonably good approximation because you don't have any data. The others would be too hard to estimate those parameters. Does that make sense?
How about if the demand is seasonal?
So that's the time varying thing, which I will talk about next time. But
Okay.
that's a great question.
Okay.
In fact, that number 3, remember I showed you 1, 2, and 3. I actually said I have
returns you were talking about, returns and repairs.
high demand variability, time varying.
Okay, you have the high demand. Okay.
No, it's the time varying demand forecast. There is a way to handle it,
Okay.
but I wanted to establish foundationally this concept. But for the concepts that with the assumptions that I've made, which is again that demand lead time is constant, etc. I've not made any major approximations or anything like that, right? I mean, I made an assumption, which is different from an approximation. But mathematically, I've not made any approximation. Do you agree?
Yeah.
Okay. So, but I think your second question is actually that hidden thing, which how do you feel? So remember the title of this class is MEIO, which is multi-echelon inventory optimization. And I also said it's a very, very complex thing to do. In fact, I can assure you, if I did that, if I solved it through an algorithm other than listing out every single option, I would be probably the most famous mathematician in the world right now. Let's just go what we've learned. So this part is right. Use of demand rates to model demand in a network. Right? So that's a very easy thing. Instead of using demand is 30 this month or something, I've used a rate. Just 30 divided by 30, which is 1 and 1. So I'm using demand rates. And the reason I like demand rates is I use it to calculate my effectively my when I change my effective lead time, I don't have to redo the calculations. But I've also showed you how to calculate effective lead time at a node, right? Everybody agree with that? I need a yes, no for that, at least one.
Yes.
Yes.
I've also showed you TSLs based on effective lead time and demand, right?
Right.
Yes? I'm guessing
Yes, yes. Yeah, yeah.
Yeah.
Yes.
And I've simplified a reasonably complex looking network. And honestly, you could have given me a 10 level network, a 10 echelon network, and thrown in this. I can literally put this in Excel and solve it in a couple of hours. Like even if you give me 10 echelons and 10,000 SKUs or something, I can literally do that in a couple of hours. Okay? Because I've given you the formula, right? It's a right to left, left to right. And it's just a formula. So you can imagine that putting it in Excel is not particularly difficult. But we've not learned multi-echelon inventory optimization. Because to Deepak's point, I'm not surprised that somebody from this session brought it up. I'm sure all of you would have brought it up if I'd given you a little bit more time. Is we've not told you how to figure out whether a location should be 75% fill rate or 30% fill rate or 50% fill rate, means especially at the upstream location. So all we've done, I have given you those numbers. So today what you learned is multi-echelon inventory calculation. We have not optimized anything yet. Does everybody agree? Because I've given you, otherwise it's a very simple calculation. And what bothers me, and this is one of the reasons, my motivations for wanting to teach both consultants and potential users, is that a lot of times people are like, companies are packaging things and saying, oh, we're doing MEIO, but you have to give us the lead time. You have to give us what the demand rate is, etc. And remember, we've not talked about the more complex things such as time varying or reverse flows, etc. All that. By the way, I'm so sorry I'm missing out on so many comments here. I just realized that it doesn't show up for whatever. So, but my apologies. But everybody get sorry. But you see that, right? What I'm talking about. So in the next class, we'll be talking about how to optimize it. But remember, what you're optimizing really depends on the business problem you're trying to solve. For example, if in the military, you're trying to figure out what is the lowest cost kind. I mean, you're trying to figure out what you need to place so that your airplanes are going to fly with the highest availability at minimum cost, right? Similarly, if you're doing, let's say you're selling, it's a CPG network, you're trying to figure out how much you should have while you're trying to maximize potentially your profit or your customer retention, right? So you're trying to optimize. It really depends on the business problem that you're trying to solve. And that formulation is key to is one of the things that we're going to think about. But that's not a mathematical problem as such. First, you have to understand that the business problem behind it. And we'll be going over that in the, not next class, but the class after. But we'll be dealing with more on the optimization part of it. Okay? So in the next class, what we'll be doing is we'll be looking at an optimization or a solution methodology to solve problems like this. So because people don't say, oh, I can't solve it optimally, I'm just not going to do it, right? There are lots of software packages that's commercially available, as well as researchers who are solving these problems. And there is a way, which is a really nice, intuitive way to do it and gives you a good set of solutions. So we're going to cover, we're going to learn that methodology in the next class. It's on network optimization, but it covers the methodology that we learn. We'll do model adjustments to handle variable demand. We will incorporate lead time variance. We'll talk about reverse and repair considerations, and we'll be talking about demand model optimization objectives. Is that okay? Means, have people gotten out of this class what they hope to, or at least gotten something out of it?
Yeah, it was really helpful.
Okay. Okay.
This is good, Naresh. I never did these calculations myself, so it was a good kind of.
And the best part is, look, you can actually use this in real life, right? Because a lot of the times people don't do this in real life. They basically sit down and sort of black box it. And I was at with not too long ago, I was looking at some numbers, etc., and somebody had told a client they can save 500 million or something, some ridiculous number, and I was quite amazed that when 500 million is not a number to sneeze at. And I asked them what they did, and they didn't do. They had actually had a mathematical error, and there's a black box that they were just using and saying this is what the software gave us. There was a bug in the software. Means I went through the code, and found it out. There's not me bragging about it, but my point is, if you understand this logic, you can actually do the calculations yourself in Excel to at least validate some of the output.
Yeah.
You can apply just even without any Excel or anything, the intuition behind it, right? I'm doing this, therefore it's going to give me this kind of an improvement, and order of magnitude, whether those numbers are. So you can do a lot of sanity checking, or you can do your own scenario analysis without the need for some software. So you can get value out of this almost immediately. And again, for me, case in point was I was able to find out some major issues on a $500 million recommendation that they were going to make to a client. So things to think about. Okay. In the meanwhile, if you want to pay it forward, look, definitely we're not asking for any money, and we would not accept any. But if there's any local charity or St. Jude's, or now I know this is an older slide because, Doctors Without Borders or anything like that, some nominal donation would go ahead and pay it forward if you can. If you don't, that's fine. I'm not tracking. Mentor your peers and juniors throughout your career. And if you want, you can teach this class in your organization. We'll make this content available. We're not looking for, again, this is not intended to be remunerated by any stretch. We would like constructive feedback. That could be, for me personally, that would be great. And if you have any topics that you want covered, I've been lucky enough that I've had great mentors and I've been exposed to many things. So if you want any topics but with a focus on application, because I think right now we are going to get into more, let's say, modern techniques, etc. But we'd like to have it focused on application, because we think right now the basic reason digital transformations are failing is because people are waiting too long to get results, etc. But anything you would like to say, wrapping remarks for me, that any input for me that I should take into account, anything I should improve?
Naresh, this is really, really outstanding. Thank you very much there's probably a lot of investment that has gone in from your side in creating the content and delivering this. So really, really appreciate that. Thank you, sir.
No, you're very welcome. The other classes are similar also, so hopefully people will attend. And again, feel free to provide any constructive input. Definitely not averse to any constructive criticism, etc. And I really think that I always do inventory first, and I think that's something which you may want to consider when you go deal with clients, or if you're for companies that you work for, etc. Okay, and so we'll have some again, we have a series of 7 classes. Network optimization is next, but we're going to do a method called the greedy algorithm. But there's a very intuitive way to do it. We're doing that. So I think the next 2 or 3. But if you want to attend the advanced MEIO, which is the variations you talked about, Deepak, I would suggest you attend the network optimization part as well, because
I plan to attend all of these as far as possible. Yes.
Okay. And we will make these recordings available. This one I'm a little bit embarrassed with the mistakes, so I may not make this recording, but there's a previous recording also that has better this stuff. We'll clean it up. Okay.
Thank you, Naresh, for teaching us this network optimization. I have one last question to ask. So, do you see any company just going with the Excel model, or maybe using Python, or some kind of a in-house tool to optimize their inventory and to figure out at which node what should be the inventory, as compared to implementing some kind of a software solution?
Lots of companies do it, but they use just the basic formulas that we use. They don't do anything for effective lead times. So they're just calculating that 78%, and they leave the lead time that they use would be essentially the 0% fill rate lead time from one to another. They don't adjust for that. in fact, most software packages that I've seen, only 1 or 2 companies adjust calculate effective lead time. It's actually quite disappointing to me, because I had actually told both, like 2 or 3 vendors that I worked with, this is a simple calculation. Even if you don't get it, let's just have a script which just overwrites those values. And they weren't willing to invest that time. Of course, they didn't want to. Again, they weren't as interested as you in understanding the math of it. So that aside, but I do see companies trying it, but they don't do this. The effective lead time calculation, I have no idea why it's so surprising or so hard for people to incorporate in their Excel calculations. But I've seen both consulting companies do this huge calculation in Excel and not do any adjustment. But many companies do this kind of do the calculation, but not effective lead time, nor do they do the adjustment for the fill rate and all things like that. And they also don't know why they. One of the problems that I have is when people say I want a 90% fill rate, I actually looked at it and said, wow, the margins here are pretty high. Why are we choosing 90%? Shouldn't it be 97%, 98%? And again, we'll be talking about that in the fourth point here, the objectives, etc. So I really want that, because why you have a certain fill rate is going to affect your entire optimization as well, right? Why 98%? Why not 95% or something like that? I can understand if why some people just do it for historical reasons, or they'll say something which I think is almost condescending and a little bit what I would classify as hubris. They would say, oh, the client is having a difficult enough time already. Let's just get them to this 90%. And I thought that was quite, to me, everybody's equally smart, right? Means the same order of magnitude intelligence. So why, if you can understand it, tell the client why it should be 95 and why it should be instead of 90, why is it 95, etc. So sorry if I'm going off on a soapbox here, but I
Got
really,
it. Yeah, you answered my question really well, Naresh. And I was part of the consulting engagement where the client asked me, okay, what should be my target service levels? And yeah, we can discuss more that in another class, but I did somewhat of simulation to understand what my back order cost is and what my inventory holding cost if I change my target service level. That is how I found
yeah.
the target service level should be, but would be happy to learn more from the next session how to accurately identify the target service level.
Right. And finally, it's how much money finally, the idea is to make money for the company, right? Means that is
Right.
one of 4 things. Again, a little bit of soapbox. It's either you're trying to increase your revenue. Related to that, the second thing could be you're trying to increase the profit for the company, or you're trying to decrease cost, or you're trying to improve some sort of process efficiency. But for inventory optimization is one of these 3, right? Increase your revenue, increase your, or increase your profit, or decrease your cost. That's what your inventory optimization really focuses on, at
Yes.
least mathematically. Right? So the other stuff, there are other things that we can do. That'll probably come. But we're trying to have a cadence for the rest of the year of 2 a week, 1 every 2 weeks, and yeah, hopefully it'll work. Okay.
Okay. Thank you, Naresh.
Thank you, everybody.
Thank you.
Appreciate
Thank
it.
you. Appreciate it.
Bye.
Thank you so much.